Avalara, India. And first of all, I will request Dr. Balaji, Scientist F, CTech Bangalore, to felicitate our speaker. Yeah. Shri Nandan Rao is a seasoned architect whose work sits at the cutting edge of cloud, computing, cybersecurity, AI technologies, and IoT. As an architect at Avalara, India, he has been instrumental in building the global compliance cloud platform with a core focus on designing the secure identity and access management solutions that power its entire ecosystem. He is currently focused on the AI transformation, building secure and scalable agentic AI solutions in the compliance space. Before joining Avalara, Nandan spent over 6 years at ABB, where he was a leading voice in the security of industrial IoT system. It was there that he led the groundbreaking first PKI rollout for industrial IoT use cases, a critical project that laid the foundation for secure communication and device management in the industrial space. Shri Nandan has a proven track record of implementing secure boot, TPM integration, and certificate management for devices. His work has been recognized with multiple patents and publications, including a paper on the very topic of PKI challenges in industrial networks. He is driven by a passion for proactive security, building it in from the ground up to fortify an organization's most valuable digital assets. Sir, over to you.
And welcome everyone. Thank you for being here. Good afternoon. So today I will talk about one of the industry use cases of using PKI. And this is something that we implemented in my previous organization, ABB. This is a PKI conference, so excited to talk about how we actually brought multiple technologies together to solve some of the trust problems in an industrial IoT system. So I'll start with what is an industrial IoT system. So this is a photo of a factory shop floor. You can see some devices out there, robots, drives, motors, etc. I mean, this is an AI-generated image, so it will have some of its own quirks there, but the idea is that you have multiple devices in a factory floor. I mean, this could be representing a manufacturing industry floor, or it could be an oil and gas station. It could be utilities like a water treatment plant or a power system, right? So the idea is that there is this industry workspaces where there are multiple devices connected, and these are special purpose devices. They're doing their own jobs. And not all of them are general purpose computers like the ones that we use day in and day out. Now, typically these devices and these industry areas are sort of isolated, right? They're never connected to the internet for very good reasons. I mean, these are controlled environments. You don't want your devices to be accessible to the outside network for hackers to take advantage of things of your network and control your processes, right? But industrial IoT sort of defeats that very own castle and moat sort of an environment that the industry builds, and it tries to connect these devices to the public internet, your AWS, your Azure, and GCP. Why would we want to do something like that? Why would we want to take critical infrastructure like your water treatment plants or your power infrastructure and connect them to the public internet and open it up for hacking for everyone? There must be a good business value to do that, right? And that's true, there is. So these networks, these systems are not really built to analyze how they're performing as a whole, at an individual level, at the devices level, or as a whole, at the factory as a whole. But what you can do with the power of cloud is you can pull the data out of these devices and networks, and then you can start looking at how is a factory doing as a whole? What devices are performing well and what devices are not performing well? What devices need maintenance, predictive maintenance, right? Before a robot can break, you can sort of look at the performance metrics coming out of that device and say, oh, this robot will break in 3 weeks if not maintained properly, if a part is not replaced. So you can probably go and order the part before the device breaks, and you can replace it before the device breaks. So there are multiple use cases where where you can analyze this data in a cloud environment, and you can derive business value out of it. So this is what industrial IoT is. You're trying to connect these you know, purpose-built devices that are performing together to solve some of your problems in the industry, to the public internet, to cloud. And you're bringing in data. You also have command and control. You can actually issue commands to these devices and make them perform actions based on your behalf, sitting at a cloud console, right? So this is what you're trying to do in an industrial IoT kind of an environment. So the same diagram I'm going to show in a little bit of an architectural view. By profession, I'm an architect. I always like this black and white diagrams with icons and boxes out there. So for those who are technologists here, this would be much more close to your heart than the previous diagram. So what you see here is what is called as an OT network, or an operations technology network. This is the closed network that you have in a factory, for example, right? So where you have different devices interconnected. Some of them are interconnected, some of them are not interconnected. You have robots, you have motors, you have drives, controllers, process automation systems that are working together to do something, to produce something in a factory, for example, right? Um, the boundary around this sort of says that this is a closed network. This is not really open to public. It's access controlled. Anybody cannot go and access these devices in these network for very good reasons, right? So you want efficiency in factories. You want to make sure that the production never stops. You want to make sure that the quality of what gets produced in a factory is always top notch, and there is no tampering in terms of how these devices operate and produce what is being produced in the factory. So this has been traditionally an isolated air-gapped sort of a network. And we are talking about connecting this network to the cloud. So what did a common pattern in which we decided that we'll connect these devices to the internet is to sort of put a special purpose device, what we call as an edge computing device, and make this edge device talk to internet. We don't want to connect each of these devices inside the factory network, each of your robots, motors, drives, etc., directly to the internet for very good reasons, right? They're not built to be secure and to be able to talk to the internet. They are built to perform very specific action in a factory. Of course, there are exceptions to this. You may have, for example, connected cameras out there. You may be having a monitoring system with cameras that you may want to directly connect to the internet. But in general, right, the pattern that we established is we'll have a special purpose device called an edge computing device, which is more secure, which can be hardened to be able to connect to the internet. But how do you connect the device to the internet? So another common pattern that we use is to put the edge device in what's called as a demilitarized zone. It's a network isolation practice, a well-established network isolation practice, where you have a private network called the OT network that's got no connectivity to the outside world other than only to this demilitarized zone, or DMZ. And the DMZ is the one that has internet access, right? So your edge device sits in the demilitarized zone. It can connect to the internet. And the only device that the OT network devices have access to is the edge device. So there's a layering that you're doing, a sort of a sandwiching to make sure that your factory devices are protected. Now, this edge device talks to the cloud, and typically it talks to a device in the cloud called a cloud gateway, right? That is the single entry point into the cloud from all of your industrial devices to collect the data, to process it, and to issue command and control out there. So it is the edge that makes a connection to the cloud gateway device. And once this connection is established, you can pull in the data. You can pull in the configuration information of each of your devices. You can pull in the operational information in terms of logs and how each of the devices is performing, and so on and so forth. And now that data is available in the cloud for you to store, process, analyze the data, right? And the way you offer that analysis, the storage, and the data to the outside world is by exposing it via what's called as an API gateway to the applications. And you would build these applications to do your predictive maintenance, preventive maintenance, your fleet analysis, your factory analysis, and so on and so forth. And this is where the real business value of an industrial IoT system is. So a quick introduction into industrial IoT. Now we'll look at what are the challenges from a security point of view to get this end-to-end working. The key challenge is verifiable trust. How does my edge device verify that I'm talking to the trusted cloud gateway and not to a hacker put up a computer somewhere in the internet? And how does the cloud gateway verify that it is talking to a trusted edge devices and not to any device that's trying to make a connection and send poison the data by sending false information into the cloud, right? So we have to obviously look at how do we establish that trust at these device level, at the edge devices level, and the cloud gateway level. We have to look at how do we establish trust at the API level, because your data, which used to stay in your factory all these years, there is a copy of that data in the cloud. Now you need to be able to you have to be sure, exactly sure as to who has access to that data and how is that data being used. And finally, you have to look at how is this communication secured between the cloud and the edge. So before I move on, one thing to keep in mind, right? The edge, there will be tens or hundreds or even thousands of these devices, depending on your different factories, the factory configurations, the number of edge devices you put out there connecting. So it's not one-to-one here. On the cloud side, it's abstracted. So you're talking to typically a virtual machine that hosts the cloud gateway and so on and so forth. But it's many to many is the relationship here. How do we solve this security problem? So we solve this by using digital certificates, right? What does a digital certificate offer? Digital certificates offer us the CIA triads of confidentiality, integrity, and authentication. So the first thing that the digital certificate offers us is a very strong identity, an identity associated with the asymmetric key pair and the common name associated within the digital certificate. It helps us to uniquely identify a device with its own key pair and authenticate the device to the cloud and vice versa. So it's a mutual authentication. We want the edge device to authenticate to the cloud, and we want the cloud gateway to authenticate to the edge device, right? So a certificate allows you to uniquely identify that this is a cloud gateway and this is an edge device. Confidentiality. When you use certificate-based authentication to establish a mutual TLS connection, you're essentially using the asymmetric keys associated with the certificate, the public and the private key pair, and you're doing a key exchange. You're deriving a symmetric key for that particular session to encrypt everything that goes on in between the edge and the cloud gateway. The entire communication is encrypted, and TLS also offers you integrity protection. So essentially, what you're doing by using certificates at both ends is you're creating a secure tunnel for this communication. Anything that goes on in this tunnel is a private communication that anybody on the internet cannot eavesdrop upon, right? So certificates really help you to achieve this whole thing. And on this end, again, this is a well-known internet paradigm. So if you open your web browser and go to google.com, you see a padlock icon on the top, right? So that's exactly what you see at the API gateway level. You have Google's certificate that gets downloaded and verified at the time of the TLS connection set up between your browser and google.com. And then it says, okay, this is a verified certificate. You are really going into google.com and not to some hacker put up website out there. So we'll not focus on the internet security. That's a typical internet security paradigm there. We'll focus more about the IoT communication security in this talk here. So we established certificates can help to secure this channel, right? But how do you go about issuing the certificates, making sure that only you can issue certificate to your devices and not a hacker and so on and so forth? That is where PKI comes into picture. That's where your public key infrastructure comes into picture. Now, public key infrastructure is, you have a question? Yeah, so the DMZ that you see there, the edge, that's where you put the fog layer, fog computing. So the whole idea about fog computing is that you bring in the computing power of cloud closer to your own industry, your own network, right? So the fog computing is not something that replaces cloud computing. Fog computing is something that you see it as augmenting your cloud computing. It's a very good question, by the way. So there are certain industries and certain customers where there is some set of data that you absolutely don't want to put into cloud at all. That's where your fog computing comes into picture. That's where you build a mini cloud with a network of edge devices and nodes. And some of that data only resides in that layer, in your fog layer. It never goes to the cloud. It never hits the internet layer. and you use those computing machines to analyze the data and take some immediate actions. A good example is those applications that are latency sensitive. You don't want all your data to go all the way over internet to cloud. Somebody get analyzed there and the commands coming back. It takes a lot of time. Whereas with the fog computing, you can do the analysis quickly there and take actions much faster than in cloud. So fog computing has its own benefit, uh, but it's mostly at the edge layer that you see fog computing. Does that answer your question? Okay. So back to PKI, right? PKI is an infrastructure. An infrastructure is like your scaffolding, right? So if you think about a building here, your foundation is a part of the infrastructure. The beams are a part of the infrastructure. If you design your foundation well, if you design your beams and trusses and your ventilation well, then you get a robust, durable building as an output. But if you design your foundation bad, you don't put the right foundation, you don't put the right pillars, you don't put the right beams in building this building, then the building is going to collapse at some point in time. PKI is exactly like that. PKI is an infrastructure that allows you to securely manage your digital certificates in any environment. But PKI is not a magic pill that's going to solve your problem of verifiable trust in an industrial IoT or any other system, right? So what I'm proposing here is, and the PKI typically comes with hierarchy. What I mean to say here is if you try to have a certificate authority that issues certificates, and you use a single certificate authority to issue certificates for every use case out there, you're setting yourself up for failure because you have no visibility into what a certificate is for and stuff like that. Whereas if you design your PKI in a way that you have taken care of separation of concerns. So you see in this example, you have a hierarchical PKI structure where you have a root CA and an intermediate CA, which are typically kept offline. You don't want the private keys of these CA certificates in the hands of a hacker, right? What you do is you have purpose-built issuing CA servers. There's one for code signing in this diagram. There's one for IoT. There's one for web and API, and there's one that you use to issue certificates to your users in your enterprise, right? Now that allows you to segment your certificate usage into different use cases, and you can leverage what's available in the digital certificate itself as usage, right? So you can issue a certificate for digital signature purpose. Now, when you have that documented in a certificate, you can't use that certificate to authenticate. You can use it only to sign documents or to sign software and stuff like that. You can issue a certificate for communication, which is what you can use for authentication and establishing secure communication. So the key takeaway from this is you have to think about separation of concerns. How do you organize your CA, your PKI hierarchy, and how do you segment your different certificates across different use cases? There's a possibility that you go very granular. You start saying, oh, I have 4 floors in my building. I'm going to issue a certificate authority for each floor in the building. Maybe that's a bit too much. Or you go at the other extreme and saying that, oh, I only need 1 certificate authority for all my use cases in my organization. That's the other extreme. And this is more contextual. It depends on your own organization and what problem you're trying to solve. But the key thing is you have to think through and do the right design for your PKI. So what PKI offers you is to automate your certificate issuance, renewals, revocation, and so on and so forth. And we'll see about that. So what did we do so far? We said we have in industrial IoT, we wanted to connect our industrial devices to the cloud. And trust is a problem in this whole scenario. So we can use digital certificates to solve some of the trust and secure communication problems that we have. And we also said PKI can help to manage the whole certificates in an industrial IoT system. All good, all solved. Life is not always so easy. So what are the challenges? Anyone, what are some of the challenges that you can think of in terms of getting to a production grade PKI environment, which is able to issue certificates and manage those? Anyone? Rotation, renewals, very good. Anything else? Okay. So the first one is of scale. Just think about it, right? So how many devices do you have in your factories or in your environment? You may have thousands, tens of thousands, hundreds of thousands, even million devices. Every sensor can potentially become a device of its own, right? We only spoke about edge devices out there in the diagram that you saw, but there are use cases where you issue certificates at a device level and a device makes communication directly. So you cannot have people going in and manually going and configuring the devices and issuing certificates. How do you provision the certificates to each of your devices? You need to really solve that automation problem. So you have protocols such as simple certificate enrollment protocol that you can use to already have a certificate in the factory when a device is manufactured. Or even at field, you can do a firmware upgrade, a software upgrade to these devices, build this simple certificate enrollment protocol, and the device goes to the CS server and gets a certificate. Those are good for the devices that you manufacture. What about the devices that you manufacture but sell it to your customers and they get provisioned in customer environment? They don't trust your CS server. They don't trust your PKI hierarchy. Your customer has their own PKI hierarchy. That's where the concept of birth certificates come into picture. So in your factory, when you manufacture the device, it goes through a certificate enrollment process, it gets a birth certificate, and the birth certificate becomes a trust anchor in your customer's environment to exchange that for a certificate in the customer's PKI. There's a very good there's a specification in the industry to talk about this. It's called 801.AR, 802.1 AR. You can read about it on how you can provision the certificates at the time of manufacturing. But this is a problem you have to solve. You cannot have manual configuration of certificates and handling of private keys in each of these systems. What's the other challenge? Your private key management, protection of your private key. If there is one weak link in this entire chain, it's this. Unless you can have assurance that your private keys are protected well in these devices. Remember, these edge devices are accessible via internet. Anybody, any hacker can try and get to these edge devices. How do you protect? If you put the private key in a file system, you're inviting the hackers to. It's sort of, putting a lot of padlocks on the front door and keeping the back door open of your house, right? So it's as good as no security. So you need to use hardware security modules. TPM is a great hardware security module that's available now in most of your laptops. Not just that, right? So you need to also control who has access to these hardware security modules. You need to make sure that there's only a single process in your software area, in your user space area, that has access to the TPMs and your HSMs and can use the private key inside of these HSM. And even if a hacker makes it to the edge device, they cannot really get access to the private key in the HSM or even the HSM, right? So this is a very key thing that most of the people miss. The other challenge, tampering. Some of these devices are, if you have a big oil pipeline, you may have to put some of these devices out in the wild, right? Anybody can go and steal these devices. So if I steal a device, can I then pluck out the HSM, try to put it in a general purpose PC and impersonate your device? Yeah, somebody's going to try doing that. How do you prevent against that? You have to build tamper-proof hardware designs out there. You have to make sure that the moment you pluck out the TPM or your HSM, it's actually killing the private key inside it. It cannot be reused once it's plucked out of a device. Not only that, but let's say your device is stolen. What do? You have to have revocation. You have to have a facility. PKI allows you this, by the way. You can revoke certificates saying that this certificate is no longer valid. The certificate was issued to a device, but that certificate is no longer valid. And if anyone tries to make a secure connection using that certificate, the connection won't go through. You cannot impersonate that device anymore. So certificate revocation lists and online certificate status protocol are two protocols that are available for you to use in case of a certificate to manage the certificate revocation. OCSP has privacy concerns. People recommend OCSP stapling now. That's another enhancement to the OCSP protocol. But the point is, in your PKI infrastructure, you have to enable these protocols, manage revocation processes, right? And then The second weakest link in all of this thing is guess what? Humans, right? You did all of these things, but you forgot to configure your cipher suites, the algorithms, the key exchange algorithms. So if you do all of this and you still do SSL v3 connections, you're inviting somebody to hack this entire thing. Anybody can eavesdrop your whole conversation. You have to take care of making sure you're hardening your edge devices, you're selecting the right key exchange protocols and the cipher suites that are used to make the connection. And this configuration is the one that usually gets ignored because nobody wants to make a decision on, oh, these are the only cipher suites that we support, right? It's the human problem. And finally, the renewal. Somebody mentioned this, right? So certificates, like everything else, expires. Do you want to issue certificates to devices that have 20 years validity? That's a very inviting thought, right? I just issue certificates and forget about it. But 20 years, I'm going to retire anyway. It's somebody else's problem. That's what happens typically, by the way. You don't want to do that. Your cipher suites are getting obsolete. Your quantum computing is going to come and destroy your keys any which way in a few years. So typically, the way things go is you would issue the leaf certificates, which are valid for 1 year or 1.5 years or 2 years at maximum, which means that at the end of expiry, somebody needs to renew these certificates. So if you have 100,000 devices, do you want somebody to go and renew each of those certificates, or do you want to automate that? The obvious answer is automation. And you have also there, you have protocols. One of them is the ACME, Automated Certificate Management Environment, which allows you to automatically renew your certificates before they expire, right? So unless you take care of these challenges, your PKI implementation would sort of give you a false sense of security, which is worse than having no security at all and knowing that you have a risk. So in conclusion, PKI can help for you to realize verifiable trust, not just in industrial IoT, but any system that requires verifiable trust across multiple devices or systems. But in order to get a robust verifiable trust in PKI, you need to take care of provisioning, automated provisioning and certificate enrollment. You need to take care of device security, protection of your private keys. You need to take care of configuration, hardening of your devices, and making sure that the right cipher suites are selected. You need to take care of revocation when the device falls into wrong hands or gets hacked. You sort of revoke the certificates and they're no longer useful. You need to take care of renewals when the certificates expire, and you need to monitor this entire system to see that it's actually functioning the way it is supposed to function. So no different from actual architecting a building well, taking care of all of your foundations and pillars and beams and ventilation and stuff like that, and then making sure that you have a robust building at the end. So when you do this, that's when you have a robust PKI implementation that you can rely upon. With that, I'm open for questions.
Hi. The 10 lakh devices you said, right? That is edge device or IoT devices?
So in the architecture that you saw, it had an edge device.
Correct.
But in reality, this could be IoT devices. Your smart camera is a very good example of an IoT device, right? It has sensors. It can be directly connected to your internet and stuff like that. So it's a combination of edge and IoT devices in reality.
We won't allow, that is what the demilitary zone, right? We are not allowing to connect to the internet.
So this is one of the architectures that you see here.
Correct.
This is an architecture that you typically see in critical infrastructure, right? But if you're doing your own home automation, you're not going to invest in an edge device just to connect to the internet. You're going to use your smart cameras, your smart lights, and your smart fans to connect directly to the internet, right? Now, those are your smart IoT devices, and those still need some form of security because one of the devices get hacked, then your entire network can get hacked. So in reality, it's not just this, right? So if you look at big enterprises, yeah, they can afford to do this. Your big factories, your car manufacturing factories, your process automation factories, your critical infrastructure, they go with this pattern. They go with this pattern. They go with the fog computing pattern, and so on and so forth. But there are small industries, there's small factories with 10 or 20 devices. They wouldn't be investing in a purpose-built edge device. They would try to connect the devices, make the devices IoT enabled, and then connect these devices. So you still need, if you're putting certificates out there, you still need everything that I spoke about as a protection mechanism there.
Okay, thank you.
Yeah. Yeah.
Leveraged from edge front, like going forward, the challenges that you mentioned,
Yeah.
like mutually exclusive, I guess. But then, do you see going forward, there are some advancements taking place at the device front as far as security concerns are addressed, or it's going to be something that we can leverage from the edge front?
Yeah, that's a good question. I mean, the devices themselves, if you think about a robot, for example, right? A robot is manufactured by specialized companies. And if you look at the way the robot gets manufactured, it's built for a specific purpose. It's built to operate on an assembly line, for example, or paint a car or something like that. It's not built to connect to IoT. It's not built with security in mind, right? Now, theoretically speaking, can we make the robot secure and capable of connecting and communicating with an IoT and directly without the edge? Absolutely, yes. But is there an incentive to do so? Probably no, right? So this is where the business dynamics come into picture. Now, to make that robot IoT capable and all of that, it's going to increase the cost of that robot. So there's a lot of pricing dynamics, the business dynamics that come into picture. Whereas an edge device is a purpose-built device for this communication. There's also an incentive on edge device manufacturers to make it more robust, make it faster, make it support more protocols. Your robot may not support your internet protocols, your MQTTs and AMQPs and TLS and stuff like that. Can we make it do that? Yes. But is there an incentive to do? Maybe or maybe not, right? So it's not a technical problem per se to solve. It's more of a business problem to solve. Technically speaking, if you keep cybersecurity in mind, cybersecurity has this concept of defense in depth. So if you go by the defense in depth, the recommendation is don't enable your robots and motors and your IoT devices to directly talk to internet. You have a layer in between where the edge device can withstand some of the attacks, and you isolate your devices. That's the only technical cybersecurity advice that someone can give. But nothing stops these devices from directly connecting other than the business dynamics.
Hey, hi Nandan. That's a very good talk. My question is because you talked already about defense in depth. So, what can be the alternate? Like, if you're not able to build in all the devices, building the PKI infra is not that easy, right? So, what can be the alternate solution? And if there is a PKI, what can be the defense in depth solution? I mean, what additionally we can bring as a defense in depth to?
Yeah.
Uh,
Good question, actually. So PKI, as you saw, has all this quirks that come with it, right? The certificate management, your revocation, and stuff like that. It again depends on scale, right? If you have a few tens of devices, you don't have hundreds of devices. So the cloud providers offer you multiple other authentication and encryption mechanisms. For example, Microsoft Azure offers you what's called a SaaS token, right? A SaaS token requires you to authenticate in a different way rather than using a digital certificate. You could still create this tunnel that you see in between, an encrypted tunnel, and you could go with it. These require mostly manual configuration and stuff like that. When you're talking about the scale as we saw here, that's when certificates really make a huge difference. The whole automation that PKI offers you, the certificate enrollment, revocation, and stuff like that, that makes a huge difference. So If you don't want to go with PKI because it involves upfront investment, it takes time to deploy all of these things and stuff like that, you can always work with things like your SAS tokens. OAuth is another protocol for authentication, right? So you can keep your authentication and secure communication as two different things. You can use OAuth. OAuth 2.1 is a newer version of the OAuth protocol, which allows you to do what's called as client credentials, where each device gets its own credentials. You still have the problem of saving and securely storing the credentials somewhere. You need to still solve that. But with that, you can do an OAuth flow with an authentication provider, and you can get a token, what's called as a Java Web Token or JWT, and then you can use that to authenticate to your cloud gateway and use that to negotiate a secure tunnel to do your communication. So there are options available beyond the certificate, but all of these options are limited to when you have limited number of devices and connectivity that you want to do, and you're okay with some kind of a manual work for people to do to maintain this whole thing. But if you really want to deploy this at a scale, you want to automate this, PKI and certificates is the way to go.
Yeah, thank you. And again, I think compatibility will also become an issue when we will be going with the OAuth and the JOT token.
Yes.
Yeah.
Yes, you
Because
need
we
to
are
have a
dealing
strong.
with the OT network.
Yeah, you need to establish the trust between your identity provider and the cloud in that case. That's true.
Thank you.
Welcome.